In this video, we're going to take what we know about position time with a constant velocity and also velocity time with a constant acceleration, and a third equation that we're going to derive intuitively by thinking about average velocity. We're going to put all of that together and we're going to derive two new equations, an equation for distance in time with constant acceleration and distance in velocity with constant acceleration. Before we get started with this, I just want to note that deriving equations in physics is a very common thing. We take simpler equations and combine them in different and unique ways to make new equations to help us understand a particular situation or a more complicated phenomenon. And that's exactly what we're going to be doing in this video. There's going to be a lot of math, and you need to pay attention and make sure you understand the math as you go. If we get to a point where you don't understand the math, chances are you're not going to suddenly start understanding it on a later step. So make sure you go back, work things out by hand on paper if you need to, do whatever it takes to understand each step as we proceed, and then the final result will make a lot of sense to you. All right, as we begin, we're going to review some of the definitions that we've developed in previous lessons. So first of all, let's review the definition of velocity. Remember, velocity is defined as the slope of the position time graph and can be calculated by finding the change in position over the change in time. Remember, this is a rise over run equation for a line, so this is actually calculating the slope of the line on a position time graph. Another way to write this is in its slope-intercept or point-slope form. That's what I have here. In a sense, it doesn't really matter which version of the equation you choose because they're both going to graph the same on a position time graph. However, we'll be using the point slope form throughout this lesson because it's a much easier version to work with. And we're also going to rearrange the point slope form to an entirely different form that's neither the definition of slope or the point slope form, but just a convenient form for us to work with as we derive. So pay attention to that a bit later. It's important also to note that this is not an acceleration equation. The definition of velocity as the change in position over time doesn't incorporate acceleration at all. And in fact, this equation by itself isn't able to deal with an accelerating object. It's only allowed to give us the slope of a position time graph for an object moving at a constant rate. If we use this equation with an object that is accelerating, so here you can see the position isn't changing over time at a constant rate anymore. The position is changing at an increasing rate. That means that we have acceleration happening. So what use is the definition of velocity equation in this case? There's really only one way to use it, and it's not really a great way for describing the motion that's actually happening. Here's what I can do. I can pick 2 points. I'm going to pick my origin and the point at 4 seconds, 80 meters. And then I can connect those 2 points with a line. And if I find the slope of that line, which is what I'm able to do using the definition of velocity, able to find the slope of a line on a position time graph, that slope of that line gives me what's called the average velocity. That means it's the velocity that the object would have to travel at a constant speed to get from the first point to the second point in the amount of time given, or to get from 0, 0 here to 480 in that 4-second time frame. Now notice that I'm calculating a straight line distance time curve, but actually the object isn't moving anywhere near the straight line that I have. So I can't actually predict where the object is going to be using my constant speed equation or my average speed equation. Again, limited usefulness. The only thing I can really do with this is calculate what the velocity of the object would have to be if it were traveling at a constant speed, even though it's not. Let's compare these two graphs for a moment. The graph on the left is showing an object that's moving at a constant speed. Notice that each of the data points is increasing by the same amount each time for every second. The graph on the right is showing an object that's obviously accelerating, but we've just gone ahead and calculated an average speed on that graph. Now let's do the actual calculations to figure out what our speeds are comparing these two graphs to one another. On the left, let's calculate the speed between the origin and the point 120. Okay, so to do that, I'm just going to plug in my values. 20 meters, the distance minus the original distance, which is 0, divided by 1 second minus the original time, which was 0, is going to give me my velocity of 20 meters per second. Interestingly, regardless of where I calculate the velocity from on this graph, I could use different time intervals. I can use different reference times. I could start at 1 second to 3 seconds. I can start from 0 but go all the way to 5 seconds if I want. Regardless of where I calculate the velocity will always be the same because this graph has a constant slope. Now, I didn't say this was a graph of a constant. I'm saying it has a constant slope. It doesn't matter where I calculate that slope. The slope is always the same. Not true of a position time graph with acceleration. When there's acceleration, the velocity is constantly increasing, so I can't just calculate a single velocity to describe the motion of the object because the velocity is constantly changing. The best I can do is use this equation to calculate the average velocity between a set of points that I choose somewhere on the graph. Now, I said before that your choice of reference point doesn't really matter, and truly it doesn't. The object is moving the same way. It has the same acceleration regardless of the reference point you choose. However, when we're talking about calculating average velocity, your different choices of reference points does actually make a difference. Depending on which points you choose, you're always going to have different velocities because your line will have different slopes on this graph. It's important for you to realize that average velocity is very limited in what it can describe. It actually only tells you what's happening between one set of points at a time. So let's go ahead and calculate that average velocity demonstrated by that red line on the right-hand graph. To calculate that velocity, I'm going to find the slope between the origin, and it looks like the point 480. So I'm going to go ahead and just set up my velocity equation, plugging in the values from those 2 points. Again, this is the rise over run equation. And it's going to be 80 minus 0 over 4 minus 0, which is going to simplify to 20 meters per second. Now, shouldn't surprise you that looking at these two graphs, the slope on the left is same as the slope on the right. But consider this. The point at 480 on the graph on the right is the only point that will produce this average velocity for the line that passes through the origin also. There's no other point on this graph that if you found the average velocity between the origin and that other point would have the same velocity as this one does. Okay, so average velocity is very unique to the set of points that you choose. Whereas before, a constant velocity is just going to be the same regardless of where you calculate it on a graph. Before we move on, I just want to mention there is a special notation we use when we're talking about average velocity versus constant velocity. Constant velocity would just be shown with a v or a vx, like I have in the equations on the screen right now, especially the ones on the left. I'm going to change the equations on the right to note that we're talking about an average velocity. And what you do is you simply draw a line over the variable to illustrate that we are calculating an average value, not a constant value, and this is only useful between the 2 points that it was calculated for. Now, if this is such a unique value to those 2 points, is it even useful for us? Well, it is useful because of a trick that we can consider when we look at the velocity time graph for our accelerating object. This is the velocity time graph showing motion of the object that's moving at an accelerating rate in the position time graph on the left. So notice that at 0, it's moving at 0 meters per second. At 1 second, it was moving at 10 meters per second. At 2 seconds, at 20 meters per second, and so on. So as you look at the graph on the right, just understand that that is a graph of the motion showing the same thing as the graph on the left. It's just the one on the right is a velocity time graph instead of a position time graph. An interesting thing to note is that our velocity time graph that we have drawn here does what our average velocity equation could not. I can pick any time on this velocity time graph, and it will tell me the associated speed that our object is moving exactly at that time. So for example, if I pick the time 1 second, I know that our object is moving 10 meters per second because that's the corresponding velocity to that time. If I pick 2 seconds, the object is moving 20 meters per second. And that's helpful. Remember, if I were to try to calculate the average speed at 1 second, I would have to calculate the slope of the line between 0 and 1 seconds, and it would give me the average speed required to get to that point in that amount of time, but it wouldn't tell me the speed that the object was actually moving at 1 second, just how fast it would have had to have gone if it was moving a constant speed the entire time. Okay, so the velocity time graph actually gives me a lot more specific information than my position time graph does with that average velocity equation. But let's go ahead and consider this a little bit further. Using this velocity time graph with a constant acceleration, I can calculate the acceleration the same way that I could calculate the velocity from a position time graph if there was a constant velocity. I just find the slope. And that's exactly what I'm able to do here using my acceleration equation from the rise over run of a velocity time graph. So if I plug in a couple of values, and remember, because this is a constant acceleration, it doesn't matter which values I choose as long as I'm finding the slope of the line between them. In this case, let's just use the same points I used on the graph on the left. So we're going to do from 0 to 4 seconds. At 0 time, my velocity is 0 meters per second, but my velocity is increasing constantly, and by 4 seconds, my velocity has increased to 40 meters per second. I'm going to go ahead and plug that into my equation. And when I simplify this, I see it's just 40 divided by 4. When I simplify that expression, I find the acceleration is 10 meters per second, or 10 meters per second squared. When you look at that velocity time graph, that should make sense because we see that for each second, I gain 10 meters per second over the previous second. So 10 meters per second squared is the calculated slope of that line or the acceleration of this object. So here I have this velocity time graph showing my object is accelerating at a constant rate of 10 meters per second squared. In the left-hand graph, I can see from the actual curve made by the points that I have an object whose position is increasing by an increasing rate over time. So we know these two graphs are related, but how is that average velocity related? Well, let's do that next. I'm going to just view from 0 to 4 seconds on these graphs because remember, I calculated that average velocity at 4 seconds. I could have calculated a different point. I chose to do 4 seconds. That was kind of an arbitrary choice on my part. But let's take a look just from 0 to 4. And here I'm going to plot my calculated average velocity on the velocity time graph. Now notice that because it's an average constant amount, remember that I just calculated as if the velocity were constant between 0 and 4 seconds. When I can see from the actual velocity time graph that the velocity was changing between 0 and 4 seconds. Now, a couple of things to notice. First of all, notice that this graph starts at 0, 0 for the actual velocity. My object had an actual initial velocity of 0 meters per second. That's going to be important because the particular relationship I'm going to show you now only applies when your initial velocity is 0, okay? And notice that it's increasing at a constant acceleration to 40 meters per second. So I started at 0, I went up to 40, and notice that my constant velocity horizontal line cut across at 20 meters per second halfway. Or another way to think about that is if I double the constant velocity value that I calculated between 0 and 4 seconds, it would tell me what the actual velocity was at 4 seconds, at exactly 4 seconds. And that's how constant velocity calculations will always work if the initial velocity is 0. When you double that constant velocity, you're going to get the actual velocity at whatever time t is. In this case, it's at 4 seconds. To help explain the math here, if I look at these two shaded regions, I'm going to shade the area on the graph between the actual velocity time curve and the constant average velocity time curve. Notice that the first triangle is below my average velocity line, and the second triangle is above it. We can think of the first triangle as negative because it's below, the second triangle as positive, it's above. And notice that if I were to add those areas together, that they would perfectly cancel each other out. That's what average velocity does. It calculates this middle value between the initial starting velocity and the final velocity. It gives me this middle value that I could use to approximate how fast the object would have to be moving at a constant speed to make it to the same distance in the same amount of time. That middle value always ends up being halfway between the maximum value, in this case 40, and the minimum value on the y-axis, which in this case was 0. That's why if I double that value, which is halfway between the maximum and the minimum, it's going to give me the maximum. I'm taking the halfway value times 2. Important to note, this only works if I have a constant acceleration. Because the velocity time graph is a straight line that's being cut across by the average velocity, I'm able to draw those two triangular shapes. If my velocity time graph were a different shape because I didn't have a constant acceleration, I wouldn't be able to mathematically work things out this way. Now let's look back over at the position time graph for a moment. Remember, velocity is the slope of a position time graph, and you can see that on that red line, we could calculate the specific slope. We did calculate it. It's 20 meters per second. Well, look at what happens if I plot the actual curve that goes through the points on the accelerating object. Notice that its slope at that 4-second mark is greater than the slope of my average velocity line. How much greater? Exactly 2 times as great. So that instantaneous speed at 4 seconds is twice as great as the slope of the average speed, which is the same from 0 to 4 seconds. And this ends up being a relationship that we can use. Okay, let's take a look at the entire graphs once again. But this time, we want to consider what would happen if we didn't start with a velocity of 0. What would happen if my initial velocity was actually a positive or negative value? In this case, we're going to look at a positive value. So here's how I'm going to do that. I'm going to shift these graphs over to the left by changing which time is my reference time. And I'm just going to make 1 second my new starting point, and I'm going to label that 0 seconds and start counting up by 1 second from there. Let's do that to the left graph first. I'm just going to shift the whole thing over. Okay, I've lost one of my points. It's somewhere to the left of the x-axis now. But now notice that I'm starting partway up the parabola, and that means that I already have an instantaneous slope. I have a speed at the very beginning, an initial speed. Let's take a look at what that does to the velocity time graph. If I shift that graph on over, now you can see that my speed starts at 10 meters per second and then continues up to 50 meters per second at 4 seconds. By 5 seconds, my speed is off the charts here because I only made my graph go up to 50. Now I'm going to consider a different average speed on my left-hand graph. Before I went from 0 to 80, but now my 0 point isn't even on the graph anymore. So instead, I'm going to start at 5 and go up to 125, or from 0 to 4 seconds on this new graph. I'm going to find the slope of that distance time curve. Notice that my velocity, though, stays the same because I'm still using this velocity time graph for the same moving object. I just shifted the graph over to the left a bit. So my velocity time graph is going to have the same slope. The acceleration is 10 meters per second squared. But on the distance time graph, I'm going to have a different average speed because I've selected a different set of points. And it's very, very likely if I selected a different set of points, I'm going to have a different speed because each set of points is pretty unique. So let's see what I calculate as my average speed here. Well, The average speed is going to be 125 meters minus my original distance, which was 5 meters. And then my change in time is 4 seconds, 4 minus 0. If I calculate that out, it's 120 divided by 4, or 30 meters per second. Let's go ahead and plot that on our right-hand graph. Do you notice any similarities between this velocity time graph and the previous one? Let's go ahead and actually calculate the acceleration from the velocity time graph of the actual motion between 0 and 4 seconds. So if I just go ahead and calculate, I notice that I have 50 meters per second at 4 seconds minus 10 meters per second at 0. So 50 minus 10 is 40 divided by 4 gives me 10 meters per second squared, just like I expected. Okay, but here's what I'm going to do. I'm going to draw a horizontal line across at my VO value. My original velocity is 10, and then the acceleration is causing the line to increase by 10 meters per second every second beyond that. Here I'm going to put in those blue triangles once again, all the way from 0 to 4, and notice that I have the same phenomena as before. But this time I can't say that my final velocity, the actual final velocity of this moving object, is twice as big as the average velocity because I had an initial velocity of 10 meters per second. So notice that it's twice as high above my initial velocity compared to the average velocity, but it's not 2 times the average velocity because 2 times 30 would be 60, and that's incorrect. Is there a mathematical relationship we use to calculate how the average velocity relates to the initial and final velocities? Well, actually, there's a couple of ways you could do this. The one that we're going to use is this. Notice that the average velocity is the final velocity plus the original velocity divided by 2. That sounds like a pretty good expression for calculating an average. If I add 2 values and then divide by 2, another way to consider this is that 2 times the average velocity equals the initial velocity plus the final velocity during your time interval. So in this case, we would add together 10 plus 50 at 60, and that's equal to 2 times the average velocity. 30 times 2 is 60. Both of these equations work. Now I'm going to direct your attention back to those mathematical expressions near the top of this slide. See again there I have 2 versions of the velocity equation relating velocity to position and time. And remember that that graph that I can make from that equation on the position time graph is always a straight line. Those equations are not well suited to dealing with acceleration, where the rate at which position changes over time is actually changing. The rate of change is changing, and I have a parabolic shape instead of a linear shape. So we need to do something to those equations to note that by themselves, they're not enough to deal with acceleration. I'll never use the average velocity time equation to predict points along the curve of an accelerating object, because it's only able to give me an average value, not the actual value. It's also not even able to help me calculate the actual speed of the object by itself. I have to use this other equation for average velocity, one that includes an initial and final velocity, to help me relate my average velocity equation from above to an accelerating object. So that's why I have to bring this second equation along with. And then the last equation I'm going to need is the equation that describes velocity time with acceleration. And that's the definition of acceleration, or the slope of the velocity time graph. Again, this is a rise over run equation. And I can write this in slope-intercept or point-slope form as well. At this point, we're going to clean things up just a bit, and then we'll get started with our derivation. Notice that I removed the actual slope form of the first equation and replaced it with the point slope form, which is a little bit easier to use. I'm going to do the same thing with the acceleration equation, remove the slope form and change it out for the point slope form. These are the 3 equations we're actually going to be using to derive some new equations. Now we're going to combine these 3 equations, and if we're looking for an xt graph, a position time graph with acceleration, We want to have acceleration in our equation. We want to make sure that we have the final position in our equation. The things that we want to get rid of, we don't want average velocity and we don't want the final velocity because neither of those are in the expression that we're looking for. We're looking for position and time with acceleration. So in order to make that equation, I'm going to need to combine these three equations in such a way that average velocity and final velocity cancel out. Well, let's see. If I begin by combining the first two equations, see I have my expression written out for average velocity equals Vx plus Vxo divided by 2. I could just go ahead and plug that directly in for Vx in the first expression. So watch, here I'm going to combine those two expressions with each other. And now I have a new expression that no longer has average velocity in it. I also want to get rid of Vx, but I still have Vx in this new expression I wrote. So what can I do? Well, I can replace that Vx with that final equation, which is the point-slope form of my acceleration equation. I'm just going to plug in that entire right-hand side of the equation instead of Vx. And there we go. Now I've got a really complicated equation that I can simplify a bit. The first thing I'm going to do is combine like terms in the numerator. I have Vxo, and then later I have another plus Vxo. So up in the numerator, I have 2 Vxo. And now I need to get rid of this extra t minus to term on the outside of that fraction. And the way that I'm going to do that, I can picture that t minus to as being like over 1. And then I can just multiply the two fractions together. Whenever I multiply an expression, 2Vxo plus ax t minus to, by another expression, I actually need to distribute that expression to both terms. So once I've actually multiplied both terms by t minus to, I get this even more complicated looking expression at the bottom. But actually I did simplify it a bit by distributing that t minus to in. All right, continuing to simplify this, I can split it into two separate fractions, each with the denominator 2. That's what I'm going to do next. And that actually makes it a little easier because I see that the middle term, I have a 2 in the numerator and a 2 in the denominator that I can cancel out. Now, just to make this look a little simpler, because this looks pretty complicated, I'm going to do a little trick that will simplify the way that we're writing this without actually doing any math. Right now we're saying t minus to an awful lot, which is fine. That's the time interval. That's how you calculate time interval. We also refer to that as delta t. Well, I'm actually just going to, instead of using delta t or t minus to, I'm just going to use t to mean the time interval. And if you have to actually calculate a change in time, you'll just have to remember that that needs to be done. But the reason we're doing that is just because it simplifies this expression enough to make it look a lot simpler and easier to use. So I'm going to change all of my t minus to's to just t. And then I'm going to divide that middle term so that I cancel out the 2 in the numerator and denominator, and I'll be left with this expression. X equals and again, that's final position, equals the original position, plus the original velocity times time, plus 1/2 the acceleration times time squared. Now, I thought we weren't supposed to have velocity in this. The reason that that's there is it's an initial condition and it's necessary. Anything that's an initial condition has to be in the equation. So my initial position makes a difference. My initial velocity makes a difference on how far I'm going to travel. And then acceleration should be a constant value. And a lot of times when we use this, we'll be calculating the acceleration or we'll be calculating the final distance. But we can use this really to calculate any variable in the equation. All right, and does it make sense that this equation is the one that we will be using to describe a parabolic phenomenon? Does it make sense that this second degree equation is resulting in a parabolic shape? And that, yes, absolutely, that should make sense because we know that a parabolic graph is a graph of a second order function. So that totally makes sense. That's what we would expect. All right, now let's work on our position velocity equation. We're going to have to combine these differently to get position and final velocity out. So in this final equation, I'm going to want to keep final velocity, Vx. I'm going to want to keep position, x, and acceleration because I know there's constant acceleration. What we really want to get rid of is average velocity because we don't want that in our final expression. And I want to get rid of time. Well, how am I going to get rid of time? I need to substitute out time when I combine these equations. And to do that, I'm just going to solve the bottom equation for t minus to. If I rearrange terms and solve that, I get t minus to equals vx minus vxo divided by the acceleration. And if you look and do the math yourself, you should see that that is a correct rearrangement of that equation. And now that I know what t minus to equals, I can go ahead and substitute that right-hand side of the expression in for t minus to in the first expression, and that gives me a bit more complicated equation that we need to simplify. But before we start simplifying, I see that I still have an average velocity in there, and I'm going to go ahead and substitute that average velocity with the second expression, the right-hand side of that second expression. And now we have a full expression that we need to simplify that has all of the values that I want in it. To simplify this, we're just going to multiply those two fractions. Multiplying the denominators is a piece of cake because we just multiply straight across. I see on the bottom I have 2 times the acceleration. In the numerator, though, I see I'm going to have to use a more advanced mathematical technique. I'm going to have to FOIL those two expressions. So first I'm going to multiply together the first values. So I'm going to have vx squared. Then the inner and outer values, I'm going to have plus vx vxo minus vx vxo. And then I'm going to have to multiply together the last expression. And that's going to be negative vxo squared. Okay, so when I do all of that, I will end up with this expression. This can be simplified because notice that I have vxov minus vxov. So those will cancel out. And then also, I need to remember to bring down the x that's on the left side of this expression, way to the left of the left-hand equal sign. Okay? And right away, I'm just going to move xo onto the other side. So it's going to be x minus xo. Make sure you understand what this step does. I just got rid of that redundancy in the numerator where I had something minus itself. And on the left side of the equal sign now, I have x minus xo. I'm going to try to get vx on a side by itself. So how am I going to do that here? Well, I'm going to multiply both sides by 2 times the acceleration. Now I'm very close to having vx on a side by itself. The last step is just to add vxo squared to both sides, and that gives me my velocity distance with acceleration equation. So notice I just left vx squared on that left-hand side. I will have to remember to solve for vx, I'm going to have to find a square root value of the expression on the other side of the equal sign. And that gives me the typical form of the velocity, acceleration, and position equation. All right, now let's just make sure this equation makes sense in context. Because it's a little odd to have like a square or a square root expression. So let's make sure that the square root expression makes sense. First of all, let's just consider a position, time, and velocity distance graph together. We know the position time graph makes sense because if something is accelerating, as time increases, its distance is going to blow up. It's going to become very large, and it's going to keep increasing per unit of time. Another way to think about this is the rate of increase is increasing, and that's what a parabola is. The jumps get larger and larger and larger per second. Distance time or position time is pretty straightforward to visualize. But what about velocity position? Notice I have position along my x-axis, which means it's the independent variable, And then velocity is going to be dependent. It's going to depend on how much position has been covered, how much distance has been covered by my moving object. Now, if this object is accelerating, think about what's going to happen. How much speed is the object going to gain over the first meter of distance? Well, because the object is probably starting slowly or even at rest, during the first meter, an accelerating object is probably going to gain quite a bit of speed because it has more time to do so. Time is not on the graph, but just think about it. As an object starts to accelerate through the first meter, it has quite a bit of time to get through that first meter. Between the first and second meter, the velocity is going to increase less because the object is moving faster and it's not going to take as much time to cover that second meter. So the object doesn't have as much time to accelerate during that first and second meter. From the second meter to the third meter, the object's moving even more quickly, so is going to accelerate less in that time. It's going to continue moving a faster speed, but it's going to gain less and less speed per meter the more meters that are covered and the more the object has a chance to accelerate. What is that going to look like? Well, it's actually the positive square root graph. And we can see that as more and more distance gets covered and the object speeds up, it's able to accelerate less and less for each meter that's covered. Now, keep in mind, if this were a velocity time graph, we would have the velocity moving up at a regular amount for each unit of time. It would be a linear graph, whereas when we compare velocity to distance, we see that it's this positive square root graph. And this has been our complete lineup of stock equations for calculating the position, velocity, acceleration, and time related to moving objects that we're going to be using all year in physics. Once again, those include our constant velocity equation, which can be used to calculate the position that something moves over time if it's moving at a constant speed. Remember, this has very, very limited use because it doesn't work to calculate with an object that's accelerating. You could potentially repurpose the average speed equation, which is the same as the constant speed equation. It assumes that an object is moving at a constant speed. You could repurpose this equation to find out information about accelerating objects, but you need to do some extra thinking steps. Caution should be used when choosing these two equations, because if you use these with accelerating objects and you don't consider how you're going to repurpose these for accelerating objects, you're probably going to analyze situations involving acceleration incorrectly. These can be used correctly with acceleration, but you need to make sure that you're thinking things through very carefully. The equations that are meant to deal with accelerating motion are our velocity, acceleration, time linear equation. This is useful when we're interested in velocity, acceleration, and time information, or we're given those variables. We now have our new equation for position, acceleration, and time. This can be used to predict the position of an accelerating object after a certain amount of time, or if we know the position after a certain amount of time, we can go back and calculate what its acceleration must have been. That's very useful for finding the acceleration if we know the positions of an object. And then lastly, we now have our equation for velocity, acceleration, and position. And we can rearrange these equations, combine them, use them in different ways that make sense as long as we are obeying the rules of algebra and plugging in the correct values that are known to solve for the values that we need to know.